Hi everyone. We were kind of sort of introduced to propositional logic last week when we talked about those four types of valid arguments. But chapter 12 and chapter 13 are really the main presentation of propositional logic. Okay? So today we will study chapter 12. It introduces us the language of propositional logic. Okay. What is the language of propositional logic? It is not an ordinary language like English or Korean. It is an artificial language that logicians made up for the purpose of articulating the logical structure of a language. Ordinary languages are sometimes very unclear about logically relevant structure of statements. So logicians devise this artificial language to compensate such defect. The language of propositional logic is really very simple. Okay? So we will learn the language of a propositional logic today, and eventually we will get to the question about determining the validity of any argument stated in propositional language. Okay, that's the content for chapter 13. But this week we will work on chapter 12 and the language of propositional logic. Okay? The language of propositional logic contains primitive symbols. Primitive symbols are P, Q, R, S, and these alphabets symbolize simple statements in English. For example, different letters symbolize different simple statements, such as P may symbolize snow is white. Okay, that's a simple statement, and P, a letter P, can symbolize that. Q may symbolize, you name it. For example, John is tall, and so on. Okay, so these alphabets, okay, these capital letters symbolize simple statements in English. Okay? And in addition to these primitive symbols, we have connectives in the language of propositional logic. There are 5 of them. And this tilde, okay, sign is called negation, and it corresponds to not in English. Dot is called conjunction, and it roughly means the same as and in English. The wedge sign is called disjunction, and it corresponds to or in English. This horseshoe sign is conditional, okay? And it symbolizes the connective, hypothetical connective if-then. Finally, there is triple bar. It's called biconditional sign, triple bar, and it symbolizes if and only if in English. Okay? specifies the necessary and sufficient condition. So we have primitive symbols and these 5 connectives to connect those primitive symbols. Okay? And these are the only symbols that we are going to need in the language of propositional logic. Okay? And there is a rule about how to combine these symbols. We can combine simple propositions, simple statement PQRS with the connectives. By combining those, we can generate more complex propositions. So if you ask, what are the kind of things that we can say, we can grammatically express in this language? First of all, we have simple propositions. Okay? Socrates is bald and snow is white. So these are, let's say, you can say like first level. Okay? These are the kind of things that we can say at the first level. You can say more complex propositions, such as you can, for example, combine P and Q with dot, for example, and generate this. Okay? So in addition to P, Q, R, S, we can also say in this language things like P and Q. Okay? That's a legitimate thing to say in this language. Another example, you can combine R and S with the connective disjunction and construct this complex proposition, R or S. Okay? These are the kind of things that you can say, let's say, second level. Can you go further? Of course. Once you have gone at this level, you can combine any statement that has been connected so far, and you can generate more complex propositions. For example, you can combine these two with the horseshoe, conditional sign, and generate complex proposition like that. This is a legitimate thing to say in this language. Okay? P and Q. If P and Q, then R or S. Okay? These are all grammatical. This is third level. Okay? But then you can go on and on. Okay? So even though we have a very primitive, limited primitive symbols, we can generate very complex propositions in this language. Let's look at some ungrammatical sentences, expressions that should not be allowed in this language. For example, P dot wedge Q. This is not grammatical sentence. Why? Well, there are two connectives between P and Q, okay? Da and wedge. And we really don't know which is the connective that connects P and Q. Is it dot or wedge? It doesn't say, okay? So this is not grammatical. So there should be only one connective in between P and Q. Okay? So we should not write this. How about that? P dot R wedge S. Is this grammatical? The expression as such is ambiguous in that it can mean this. Okay? In this case, it's really saying P and R that or S. Okay? That's what this means. Okay? When the parentheses goes around here, it says this one or S. So when this is interpreted as saying that, this is basically a wedge statement. Okay? Basically a wedge statement. But when the parenthesis goes around here, okay, it says P and R or S. So this is really a conjunction statement. And without the parenthesis properly placed, this can mean either that or that. So it's ambiguous, and we should not allow statement like that in the language of propositional logic. Okay? So it's like saying this is like it's like really like this: 2 plus 3 multiply 4. Okay, this is not a grammatical in mathematical expressions. Okay, because it can mean 2 plus 3. Okay, that is multiplied by 4. Or it can mean 2 plus 3 multiplied by 4. Okay. What's the value of this? 5 times 4 is 20. 14. Different values. Okay. So depending on where the parenthesis goes, it makes a big difference. So you have to place either this way or that way. You have to disambiguate this. Okay? All right, so those are some ungrammatical sentences. In the book, you will frequently come across expressions called truth values. Truth values is really either one of these two. Okay? A sentence can be either true or false. Okay? And these two are called truth values. So we can say a sentence can have either one of these two truth values. Okay? T or F. The meaning of connectives, let's say, P, so P, okay, proposition P and Q. Let's say, suppose there are, you can think of these as two coins. Okay? P and Q are two coins. You toss these two coins, and it can land 4 different ways. Okay, upside or downside, right? There are 2 ways a coin can turn up, okay? Head or tail. So propositions P and Q can have, P can have T or F as truth values. Q can have T or F as truth values, like a coin, which can turn up head or tail, okay? So when we consider those 2 propositions, there are 4 different combinations of truth values. For example, when you toss 2 coins, both of them can turn up heads. Okay, so TT is one possibility. P can be true and Q can be false. That's the second possibility. P can be false and Q can be true, and both of them can be false. So these are all possibilities that there are. Okay, 4 different possibilities of combining truth values for P and Q. For each of these possibilities, there are 1, 2, 3, 4. For each of these possibilities, okay, we can specify the truth value of these connectives in the following way. Okay, let's look at not P first. Not P, the truth value of not P is the opposite of truth value of P. Okay, so when P is true, not P is the opposite. Okay, so F. When P is true, not P is F. When P is false, not P is true. Okay, so what do you mean to say not P? not P. Okay? What it means is it says the opposite of P. Okay? So when P is true, not P is false. When P is false, not P is true. Okay? That's what it says. What about P and Q? P and Q, P dot Q is true only when both of them are true. So only in the first case, when both of them are true, P dot Q is true, otherwise false. Okay? F, F, F. P or Q is true only when at least one of them is true. Okay? So, in other words, P or Q is false only when both of them are false, otherwise true. Okay? So, in the first three cases, okay, you look at this, TT, TF, FT. In all these cases, P or Q is true. Sometimes this meaning, okay, which is called inclusive or. Okay, inclusive or. In ordinary English, the expression or can mean inclusive or exclusive. Inclusive or means when both of them are true, P or Q is true. Okay? That's what we will understand. That's how we will understand which. Okay? It's inclusive or. When both of them are true, P is true, Q is true, P or Q is true. But sometimes or in English may mean exclusive or in the sense that when both of them are true, P or Q is not true. Okay? That's called exclusive or. Okay? Exclusive or means when P is true, Q is true, P or Q is false. Okay? In English, or sometimes do mean exclusive sense. Right? And a mother tells the kid that you can choose either ice cream or chocolate chips. She probably means the kid has to choose one or the other, not both. Okay? The mother is afraid that the kid consumes too much sugar. Okay? So when she says ice cream, you have to eat something, but not much. So she says ice cream or chocolate chips. That means both of them are chosen, is ruled out. She's using or in exclusive sense. Right? So in English, or can mean either inclusive or exclusive. But in logic, we will just focus on the inclusive sense of or. And which symbolize the inclusive or. Okay? So when both of them are true, P which Q is true. Okay? So keep that in mind. P horseshoe Q, that is P, if P then Q is false only when P is true, that is the antecedent is true and the consequent is false. Only in that case, when the antecedent is true and consequent is false, if P then Q is false, otherwise true. Okay? Finally, P triple bar Q, P if and only if Q, is true when both of them have the same truth values, such as TT or FF. In that case, P triple bar Q is true when they have different truth values, like TF or FT, P if and only if Q is false. Okay? So when you say P if and only if Q, P and Q have the same truth value. Okay? All right, so this table kind of summarizes the meaning of connectives. It gives kind of precise meaning of these connectives. So we will use these connectives precisely in this sense, specified in this truth table. In the book, you see the expression called truth function. Okay? What is the truth function? The truth value of the whole is determined by the truth values of the components. What does that mean? Well, for example, look at this. P dot Q. Okay? You plug in the truth values for P and Q, then the truth values of the whole sentence is thereby fixed. Okay? There is only one value coming out. Okay? So when you put, let's say, T for P and let's say F for Q, then what comes out is only one. Okay? Thereby it's fixed. Okay? Going back to what? Truth table for P and P dot Q. Okay? When P is true, Q is false, the truth value for whole thing is false. Okay? It's thereby fixed. It's false. Okay? Now, when this kind of relationship holds, it's called function. Okay? The truth value of the whole formula is determined by the truth values of the components. Okay? When this happens, it's called truth function. Okay? The whole formula is truth function. It's like a numerical function. If I give you an analogy, numerical function like x plus y. Okay? You plug in a number there, let's say 3 and 5. The number of the whole thing is thereby fixed. Gives the value 8. And when this happens, we say plus is a numerical function. Okay? What comes out is fixed by what goes in. So x plus y is called a numerical function. Same thing is happening here. P dot Q. Okay, if you plug in, okay, truth values for PQ, what comes out is thereby fixed. So it's called truth function. Okay? Not all connectives in English are truth functions. But the connectives that we will have in propositional logic are all truth functions. Okay? That's the important thing. The 5 connectives that we will use in propositional logic are all truth functions. So let's look at an example here. This is truth function. That means you put truth values for PQR, then the truth value of the whole thing is thereby fixed. Okay? So you put T for P, F for Q, and F for R. What is the truth value of whole thing? Well, first, you take care of this parenthesis part first. Okay? So forget about the rest, and you just focus on the truth value of what is inside parentheses first. Okay? P dot Q is what? When P is true and Q is false. P dot Q is, you have to go back and look at the truth table for the connectives. P dot Q is false. And then you have to look at this whole thing, or R. And this whole thing is what? F. So you are really considering F or F. So again, go back to the truth table for the connectives. And F, which F is F. Okay? So we can get the truth value of the whole thing. Okay? In this way, we can get the truth, we can draw the truth table. So that's the final thing for today, drawing the truth table. The truth table for P dot Q or R, since there are 3 simple propositions, P, Q, R, there are 8 possible distributions of truth values for P, Q, R. Let's see. Actually, it's the number of rows that you have to draw is really it depends on how many simple statements you have. So here are 3, okay, P, Q, R. And in general, the number of rows that you have to draw for complex propositions with n number of simple proposition is 2 to the power of n. Okay? So we have 3 simple propositions, so it's 2 to the power of 3, which is 8. If you have 2, then you need 4 rows. Okay? If you have 4 different simple propositions, you need what? 2 to the power of 4, so it's 16. Okay? So let's draw the truth table for this this complex statement. I'm not going to draw the whole thing, but I like to give you at least how the picture look like. P dot Q or R. Okay. P, Q, R, P dot R, sorry. P dot Q, P dot Q, or R. To complete the truth table for these complex propositions, you write down the simple propositions first, P, Q, R. Okay, so and then you give a complete list of combinations for truth values for PQR. Okay? There are 8 different possible combinations. The way you do it is, for the first one, you alternate by 4. So T, 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 and then F, 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 F. For the second proposition, you alternate by 2. So T, T, F, F, T, T, F, F. Okay? And for the last one, you alternate by 1. So T, F, T, F, T, F, T, F. So this gives exhaustive list of all the possible combination of truth values for PQR. Okay? And for each of these, you get the truth value for P dot Q or R. I think we just got the truth value for when P is true, Q is false, and R is false, the truth value is F. Okay? So we already got the truth value for T, F, F, that one. Okay? The first one. So in this case, we already know the truth value for this one. That is F. And you can get the truth value for each of these cases. And you put the truth values here. Okay? And that is how you complete truth table for any complex proposition. Okay? For any complex proposition, if it's grammatical, then you can complete the truth table for that complex proposition. And we are going to need this for the next chapter. So I want you to do the practice quizzes and do yourself at least a couple of exercise problems involving these truth tables. Okay? Okay, so that's it for today.